Welcome back. We are going to start a new topic. It's on vapor power cycles. So let me just go through the objective of this particular chapter. So I will start with the analysis of the vapor power cycle, in which basically the working fluid is alternatively vaporized and condensed. It does not remain in the gas state all the time, as in the case of the gas power cycles. We will try to first analyze the particularly based on Carnot cycle, and followed by introducing the Rankin cycle, and then certain aspects of such Rankin cycles issues and how one can increase its efficiency by reheating. So let me start with the basic alternative vaporized and condensed cycle, that is your vapor power cycles in the form of a Carnot cycle. Now, Carnot cycle is the most efficient cycle which we know, which operates between two specified temperature limits. Okay. Now, that means it's very obvious that one would like to make use of Carnot kind of cycle for the case of vapor power cycle. And in this case, we can start with the Carnot cycle by considering this saturated dome, and the cycle operates within this dome. And because of the fact that the vapor cycle means for alternative vaporized and condensed cycles, or hence it has to be within the saturated dome. So that's what we made use of the Carnot cycle. We consider steam as a working fluid. Now let me just refresh the Carnot cycle, particularly in this form. This is on a TS diagram. So 1 and 2 is a process where the fluid is heated reversibly isothermally in a boiler. Okay, this is where your Q in is being supplied using a boiler, okay, at a constant temperature. And 2 and 3 is basically where the stream is expanded asentropically, having a constant entropy, okay. And 2 is your saturated vapor. It gets expanded, creating a final state 3, where it is a mixture of vapor and liquid. And finally 3 to 4 is a process where it is condensed isothermally reversibly in a condenser. That means there is a Q out of it, okay. And then the 4 it is compressed isentropically by a compressor in order to get the original state, which is saturated liquid. Now it's very clear that the Q in depends on the enthalpy change from 1 to 2, and essentially we cannot raise the temperature, because as you increase the temperature, Q in will decrease because of the fact that the enthalpy difference between 1 and 2 will decrease. Thus it limits the maximum temperature one can use in a saturated liquid or saturated dome, as in the case of the way we have demonstrated here. And we know that efficiency of a cycle increases if you increase the temperature at which heat is being supplied. So thus this limits the temperature at which we can use as a Carnot cycle. So in addition, there are issues related to the turbine, which has difficulty in operating the mixtures. Similarly, they are related to compressing the mixtures. Thus the question is Carnot cycle a suitable model for power cycle? And we know, based on our current just discussion, that there are issues related with such a Carnot operation under saturated dome. Okay. So let me just summarize this impracticalities of the Carnot vapor cycle. So as I already mentioned, that using Carnot cycle in saturated dome has impracticalities, and that is it limits the heat transfer to phase systems, okay, which is basically it limits the maximum temperature that can be used, and thus it has a limited thermal efficiency. Okay, and of course the turbine has issues. That means turbine cannot handle low quality steams. So what we prefer is 3 as close as saturated vapor line. Similarly, compressor cannot easily handle 2-phase compression, and thus we also prefer 4 to be as close as saturated liquid line. So these are the impracticalities of the Carnot vapor cycle. One can try to avoid this by considering the 1 to 2 process, that means isothermal heating process, at supercritical condition. However, the problem in this case would be that the boiler has to operate at different pressure all the time. That means the boiler has to operate at different pressure, okay, along this line, and this would be a difficult as far as the practicality goes. Okay, hence it's not so easy to do that. Second is that you can avoid, of course, this 2-phase issues of handling for the turbine from here 2 to 3, but for 4 to 1 for the pump, it is the pump has to operate at a very high pressure, because it has to compress from 4 to 1, and this is also impracticality, and hence the Carnot cycle cannot be approximated in actual devices, and it's not a realistic model for vapor power cycles. So we'll try to come up with another cycle which is more practical, and this is where we're going to introduce Rankin cycle, which is the ideal cycle for vapor power cycles. So what it does, it avoids impracticalities by superheating the steam in boiler and condensing it completely in condenser. Okay, so let me just summarize this cycle first. So here the 1 to 2 is your isentropic compression in a pump, okay, followed by a constant pressure heat addition in a boiler, followed by your isentropic expansion in a turbine, okay, which is 3 to 4, followed by as a constant pressure heat rejection in a condenser. Okay, one can describe this process on a TS diagram, and let me describe this first. So we'll start with one, which is this. Okay, so the one condition is saturated liquid. Okay, it enters the pump, and where it is isentropically compressed to the operating pressure, okay, which is this. So this is the boiler pressure. Okay, so it reaches up to 2, that means 2 is at a boiler pressure, this is at boiler pressure. Okay, and water enters the boiler as a compressed liquid at 2 and leaves as a superheated vapor. So this becomes superheated. So this is your superheated. Okay, here the turbine expands isentropically such that the P and T of the steam drops and reaches a two-phase system. So the 4 is a two-phase system. Okay, and here 4 to 1 is the steam gets condensed at a constant pressure and it leaves as saturated liquid to the pump at 1. Okay, so this is at saturated liquid. So naturally 4 to 1 is the work pump in, and this is a W turbine out, and this is your Q in the boiler, Q out from the condenser. So this is the summary of the Rankin cycle involved in this. Okay, so now we can consider the energy balances for each particular devices involved in the Rankin cycle. Considering it to be steady state flow devices, one can simply write these energy balance equations and consider each particular device. So for the case of pump, considering it to be adiabatic, okay, the work here is simply the enthalpy change between 2 and 1. So that is how the work of the pump in. The boiler, there is no work involved in that. Okay, there is no boundary work, no other work. So your Q in is simply the enthalpy change between 3 and 2. Okay. Turbine, of course, is also adiabatic, and in this case in idealized condition, and this is your turbine work out, which is nothing but your enthalpy change between 3 and 4. Condenser, there is no work involved in that, and hence Q out is simply the enthalpy change between 4 and 1. Okay. So now one can also make use of these balances as well as the overall information on the work net and calculate the thermal efficiency. So we know the thermal efficiency is nothing but the W net out divided by Q in, based on the energy balance is nothing but 1 minus Q out by Q in. Now W net is simply Q1 minus Q out is nothing but W turbine out minus W pump in. Okay. So based on the information available, one can plug in this and calculate the thermal efficiency of the Rankin cycle. Okay. Now what we discussed as of now is only the idealized Rankin cycle, but we know the irreversibilities are associated with such Rankin cycle, and the fact that many the devices involve irreversibility. So we'll just try to understand the deviation of the actual vapor cycle from the idealized Rankin cycle. So here the solid line is your idealized cycle, and the dashed line is basically the cycle containing irreversibility. So from 1 to 2, there is a deviation from the idealized or isentropic process, okay, because of the irreversibility in the pump, and similarly there could be a pressure drop in the boiler, and thus it may not be constant temperature within the saturated dome condition. Similarly, there could be irreversibility in the turbine, and hence it may not be isentropic, so that's why it follows this dashed line, and similarly there could be a pressure drop in the condenser. Based on simply the irreversibility associated with the pump and turbine, one can come up with a more simplified diagram on TS, where we just consider the irreversibility here, where from 1 and 1 to A represent the actual path because of the irreversibility, and 2S represent the isentropic path for the pump. Okay. Similarly, 3, 4S is your isentropic expansion for the case of idealized turbine, and 3, 4A is for the case of actual turbine, and due to the irreversibility it will follow this dashed line. Okay. So one can also utilize this information in the form of isentropic efficiency, which will quantify this deviation. So isentropic efficiency for pump is nothing but your ratio of the work, isentropic work, and the actual work, and this can be written in terms of change in the enthalpies. Okay. Similarly, for the case of turbine, it will be opposite. The actual work out will be less than the isentropic work. On the other hand, for the case of the pump, the actual work has to be more than the isentropic work. So that means your etas P and etas taus are going to be less than 1, and this can be related to the changes in the enthalpies. Okay. Now we have already discussed the fact that we can increase the efficiency of such cycle if we can increase the temperature at which the heat is being supplied, or decrease the temperature at which heat is taken out from the condenser, and if it's supplied at a higher temperature in the boiler. So we'll try to understand how this can be achieved within this Rankin cycle. So average fluid temperature should be as high as possible during heat addition, as low as possible during heat rejection. Okay. So we can achieve this by first considering the case of lowering condenser pressure. Okay. So let's assume that you have condenser operates at P4. Okay. And so the new pressure, if it is lowered, let's say P-4, this will increase the area, which is basically the increase in the W net. Okay. And thus the efficiency will increase. Okay. Now similarly, one can also increase the temperature at which the 3 is, that means the exit of the boiler, that means increase the temperature, superheat the steam to a higher temperature. This will also increase the network. Okay. You can achieve the same effect by increasing the boiler pressure. So either you increase this to here, or you can increase the boiler pressure, which will be the case of this. Okay. By doing that, you can also increase the W net, but of course there will be decrease in the W net, because this line, which is isentropic line, will shift to the left from 4 to 4 dash, and this is the amount which will get reduced. Okay, but this Tmax, or superheating the steam to a higher temperature, is limited by the metallurgical constraints. That means the container should be able to sustain that much heat. Okay. There is another problem due to this increased boiler pressure. If you increase the boiling pressure to achieve this high temperature, as well as to increase this work net, this 4 shifts to 4 dash, which means the moisture content of 4 dash is much higher than 4. Okay, so the quality is reduces. Okay, and this creates problem for the turbine, because turbine has difficulty in operating two-phase mixtures. Okay, so we can try to avoid it. Okay, so that means how can we take the advantage of the increased efficiency at higher boiler pressure without facing the problem of excessive moisture at the final stages of the turbine? So what we can do is we can expand this steam in 2 stages. So instead of going down here, okay, what we can do is intermittently we can stop here and just take out the steam and reheat again. So you can have this one turbine here and another turbine. So one turbine works at high pressure because this is at higher pressure, okay, and the other turbine works at low pressure because this line here, which is reheated, is at a low pressure. That's why you have 2 turbines, okay, and that's why you have this one from 2 to 3 it goes and the steam is taken out, is being reheated. The exit P5 is taken to the low pressure turbine, okay, and from here you have 6 and 6 undergoes condensation using a condenser, followed completing the whole cycle. So preheating increases the quality, okay, and reduces the excessive moisture at the final stage and increases the performance of this particular Rankin cycle. Now one can understand that there is 2 specific heat being supplied. One is at this end, which is at the primary heat, okay, which is from 2 to 3, and other one is at during the reheating process. So this is Q primary plus Q heat. It can be directly related to the enthalpy change at different points. 3 to 2 is for the primary heat and 5 to 4, okay, is to correspond to reheat. And similarly there are 2 turbines, hence here 2 work associated with that, which also can be related directly to the enthalpy change. And overall the efficiency can be written in the same way as we have written earlier, okay. You can increase the average temperature of this, because here the average temperature depends on the temperature of this and as well as here. So this whole path from here to here corresponds to the increasing changes in the temperature, and so you can take the average temperature. Now this average temperature further can be increased by increasing the number of reheat and number of expansion. So this is an idealized or kind of a limiting case where the T average is quite high, and which essentially means the efficiency will be quite high for this case. So for this you will have to increase the number of expansion and reheat stages, okay, in order to have very high temperature during reheat, okay. Or this is basically from the basic concept that we need higher average temperature of where the heat is being supplied, okay. So that will be the end of this lecture. So we'll be looking at regenerative vapor power cycle and other analysis of this Rankine power cycle, okay, in the next lecture. We will also consider something called cogeneration in the next lecture. So I will see you in the next lecture.